And then we'll take it away for section 1.3, classwork, question number 1.
I've got it. But it says host disabled participants screen sharing.
Try it again.
There we go.
Haha. So what are we looking at?
Okay, so for example 1 on 1.3, it was 4 differential equations given to us. And then basically our path to figure out which one matched each slope field was just plugging each of them into Maple. So I took the first 2 and then Emma took the second 2. And then I found that the first one, dy over dt here, equals 2y minus t, matched. It matched the second slope field in the homework, or in the classwork. And then for part B.
Okay, real quick, what are the characteristics that you're zooming in on, pun intended, since we're on Zoom? What are the characteristics that you're zooming in on in order to determine that that's a match?
Well, we can see that on the second slope field on the classwork, it looks like maybe 1/8, like the initial condition. There's like a line that goes across, and that the arrows go up and down from that.
So you're talking about what appears to be kind of like a slanted line.
Yeah.
And were you saying 1/8? Is that the slope of the line that you're talking about?
I was thinking the initial condition of.
Got it.
At one, potentially 1/8.
Got it. Okay.
That line that goes across.
So looking for kind of trend lines that you can identify. That's cool. Okay. Sorry. Proceed.
And then for part C, it says describe the behavior of the solution at y of 0 equals 2, or oh my gosh, equals 1/2. So the initial condition of 1/2. We plotted that right here. This guy right here is a line of the initial condition of 1/2. And we just said that as t approaches infinity, that also approaches infinity.
So I'm going to challenge you. Is there a way, it's not that bad, is there a way that you can make the particular solution associated with that third initial condition? Is there a way that you can make that green?
Oh, I'm sure there is. Do I know how to do it? No.
but not the other two, just that one.
I believe you can use line color.
Yep, and he's got line color on the screen, but he's saying line color equals blue, which is basically saying I want all my solution curves to be blue. So rather than all of them be blue, if you kind of delete where it says blue, back that up.
Maybe like line 3 or...
Actually, what you're going to do is you're going to use the same kind of bracket notation. And so bracket, and then the first line color will associate with the first initial condition. So you can say, make that blue, comma. The second one, make that one blue, comma. Then make that third one green. And then close your bracket. Now notice, the computer sees that as, oh, there's 3 initial conditions, there's 3 colors, I'll take them in order, right? So this is a handy tool for being able to tell the difference between your initial conditions. Because of course, you can imagine having like 10 different initial conditions and have all these particular solutions, but you're like, I want you to pay attention to this one right here. So,
Gotcha.
So cool. Congratulations.
Thank you. I'm going to stop sharing so Emma can share her screen.
Go for it. So what you got?
I believe she ended up going and doing the second or the last 2.
Are you muted, Emma?
Yeah, I just unmuted. Okay, so I plugged in the last 2 and found that the dy dt of 3y times 1 minus y was the slope on the left. And then I started changing this real quick just because you were doing that in the last one.
No, that's cool. That's a good call.
And then we'll put green again.
Yeah. It's interesting. Your arrows there. Oh, okay. Is it because you said color equals blue?
Oh, yeah.
And color equals blue changes the slope field arrows.
Right.
Line color changes the particular solutions, right? So nicely done.
So there's 3 particular solutions, and then we did the y of 0 equals a half, which is this green one. And then we said that as t increases, the function approaches equilibrium, which is at 1.
Yep. Now, this is a really interesting graph because we can talk about equilibrium as t approaches infinity, but what happens to that same curve as t approaches negative infinity?
It approaches 0.
So technically, this graph, and you can see both of them, this graph has 2 equilibrium solutions. One of them happens to be at y equals 1, and one of them happens to be at y equals 0. And if you take a look at the equation for that graph, the equation for that graph is 3y times 1 minus y. Do you see where the 2 equilibrium solutions come from in the equation? What are the y values? And I'm looking now at the PDF of the classwork. That third equation over, that's the one that she graphed for this. Do you see where that third equation, dy dt equals 3y times 1 minus y? Do you see where the 2 equilibrium solutions are coming from?
When you set it equal to 0, you would have 3 times y equals 0, and then you'd have 1 minus y equals 0.
So we don't need the slope field to be able to see those equilibrium solutions, but man, it makes them really obvious, right? So you might look at an equation and go, I don't know if there's any equilibrium solutions. Let me try taking a look at the slope field. And then when you look at the slope field, you're like, oh, there is something going on there. I wonder what that is. There's something interesting around this area. And so sometimes the slope field is the generator for being able to come up with really interesting characteristics of the differential equation. So nice work with that. Okay. So that was number 1 for 1.3. How about number 2 for 1.3? Who had number 2? Who wants to take a big number 2 for us?
That was us.
Never appropriate. Never appropriate. Go ahead. Fire away.
All right. So number 2 was asking us to look at this slope field right here, and it was asking whether or not it was autonomous. And so we concluded that it was not autonomous because as you picked any value of y, you kind of looked across all the, scroll back and forth on changed, they weren't, and that does not fit within the definition of autonomous.
So what is the definition of autonomous, since I've got you on mic?
It's when the differential equation is not dependent on the dependent variable. It was like this. One second. It's one of these things right here. So the function has nothing to do with t at all. So that means it's autonomous.
Yeah. So the differential equation, literally the equation that tells you the slope, is only dependent upon the dependent variable. So literally it's saying the slope, wherever you're at, the slope only matters. All that matters for the slope is how high you are on the graph. So what's your vertical coordinate? Because if you know your vertical coordinate, then you know your slope. So looking at that slope field that you're given for number 2, you can look across horizontally and see, oh, there's all kinds of different slopes at different horizontal locations, right? So it can't be autonomous. In other words, the slope that slope field gives depends both on where you're at vertically, but also where you're at horizontally. So nice work.
Yeah.
Okay, who wants to tackle number 3?
It's us again.
Oh, you had both number 2 and number 3. Hey, what do you know?
Yeah. We lucked out. All right,
That
so
comes
part
in
A
handy. Part
was,
A.
let me see if I can zoom out of this thing. Suppose we know that a graph below is solution to the autonomous equation, this thing, right? So here's our graph. And the question was, how much of the slope field can you sketch from this information? And since slope is only dependent on height, right, as you said, with the autonomous equation, we can sketch the slope on any value of y that we see here. So anything between the t-axis and like y equals 4.
So what would it look like? I mean, if you had to describe the slope field, what would it look like?
It would look like it took that graph and it just like ran it back and forth across the t.
So horizontal shifting, right?
Yeah.
Yeah. So every single particular solution for this differential equation, whatever the differential equation is, every particular solution is going to look like that graph, but shifted horizontally some amount, right?
Mm-hmm.
Nice work. Can we say anything about what's going on below the t-axis?
No, because we don't see anything.
Yep. Maybe there's something going on down there, but this particular solution doesn't include any of that information, right? So oftentimes in mathematics, recognizing the limitations of what you can say about something is super important. We almost never get the ability to say, this is true everywhere and always. It's usually, and notice I'm couching my language here, it's usually we get to say, it's true between here and here, or between here and here, or in this region it's true, or for certain types of input values it's true. In mathematics, we almost never get to say, yep, it's true everywhere and always for all inputs forever, right? It just, you're really lucky when you find those. Anybody know what those are called when we find statements that are universally true no matter what, as long as you follow the rules in mathematics? You've heard
Law?
it before. No, not a law. We don't use the word law in mathematics very often. There's another word that we use, and you've run into it every time. And if you've ever read a math book, you run into this word all the time.
Theorem?
Ding! Math theorems. A theorem is as universal a statement as we can make in mathematics, right? The only kind of greater honor that a theorem can have is to be referred to as the general theorem or the general theory of something. Or if you're really lucky, something like the, if you've ever run into the, there's rules in algebra, and one of them says that if you have a polynomial of degree n, it has exactly n roots, though some of them may be complex. You probably heard this before, right? Right? This is called the fundamental theorem of algebra. And so like the pinnacle in mathematics is to be referred to as the fundamental theorem. That's like, oh, that's the highest honor that can be bestowed, even higher than naming a chicken dish after it. Like General Tso's chicken, that's below fundamental theorem, right? And I don't know if you've ever had General Tso's chicken, you know that that's quite an honor. It's the highest honor that the Chinese military can bestow. It's naming a chicken dish after you. No, that's not true. Anyways, I'll shut up now. How about number 4? Nobody had number 4. I didn't assign number 4 to anybody. I wonder if we'll see number 4 again. How about number 5?
That would be mine.
Well, I mean, not just yours, but yeah, I'll take it.
I was working on it while the other two were working on the other one.
Oh, okay.
I'll share my screen here.
It's very generous.
Okay.
Oh, pretty.
So it said to graph this equation of d theta d o dt, and this is what it looks like.
Okay.
So, and there's a third line here. It's not very good.
Interesting. So there's a third solution curve that's not much of a solution curve. It just runs right along the horizontal axis.
Yeah.
Cool.
And so it said calculate the equilibrium solutions. And we came to the conclusion that for our I2 case, theta is 0. And for the other two, I'm not sure.
Okay. So Paul, just a point of order. The question 3A was saying sketch 3 different slope fields, 3 slope fields, one for each of the following values of I. And remember we put we changed the value in your equation of P. Remember and so this is a slope field, absolutely 100% correct for when in the case of I2 when it's equal to 0. And so if you were to copy that code, you'd have to do it for a different equation, right? But the only difference in the equation would be instead of that second parentheses times 0, it would be times negative 0.1 or positive 0.1.
Oh, I see. Okay.
Yep. And so you could call this one EQ1 or EQ2 or whatever you want to call it, and then do a different DE plot for the 3 different differential equations. Keeping track of all these variables and subscripts and stuff, it's a pain. It really is. But that's how we get to be exact.
Yeah. Do you want me to do those now? Or?
You can do it and then show us maybe later on. We'll have a chance to see it. So that's for part A. Part B was calculating the equilibrium solutions. And so equilibrium solution for that DE plot appears to be where?
Looks like 0.
Yeah, and so reading the graph, you would say there's an equilibrium solution when theta of t equals 0. So if you pick any initial condition that's above the horizontal axis, the t-axis, or below the t-axis, any other position, it's either going to run away from or towards that equilibrium solution over time. Another way you might say it is the limit of any particular solution as t approaches infinity, in this case, is either 0 if you start below the t-axis, or positive infinity if you start above it. Does that make sense?
Yeah.
So the graph shows us something that might not be readily apparent when we're looking at the differential equation, right? You might not be able to spot it right away. So he's going to continue filling in the gaps for that one to make the other 2 slope fields. How about 1.4, question number 1? How'd we do on that one? I know you guys were crunched for time, but did you manage to finish it?
We managed to finish most of it.
Cool. Cool. You can go ahead and share your screen or whatever it is that you want to do to show us what you got. And so for this one, I gave you a differential equation that you could totally solve without any trouble. You don't even need to use separation of variables. You just integrate both sides with respect to t.
Yeah. And so we had to cheat a little bit, and we didn't quite do it analytically. But yes, we declared our equation, and then we used D-solve, and then we got this, and then, yeah, forgetting what the questions were.
No, that's part A. You found you solve the initial value problem, which gives you a particular solution. And the particular solution is y of t equals sine t plus 2.
Yes, correct.
Nailed it.
We use Euler's method. That's what this
Excuse me?
is.
What was that? What was
Euler's
the
method?
What was the name?
Euler's method. It
What was
was
the name?
Euler's method.
What was
Yeah,
the
it's
name?
Euler's method. Euler.
No. Nope.
Euler.
Nope. Every time
saying
someone says Euler, a mathematician loses his wings. It's a terrible thing. It's like ringing
How
a
much of a
bell
wing?
in reverse. But well, I mean, we have a lot of wings, so it's just one of the things. It's a running truism in mathematical circles that if you mispronounce Euler, you will either be invited to leave or you will be mocked mercilessly thereafter. So I'm just giving you a fair warning. I of course would never judge, but if I did, I would judge harshly. So it is Euler.
So, yeah, this guy's number.
Yeah.
He said, hey, why don't you type this thing into Maple? And so I did.
Cool.
And told me that personally, actually. And so we did. And then I asked Maple to show me all the steps. And so it did, because it's really nice like that. And if you come down here, you'll notice that Maple's solution was exactly the same as my solution that we got up here. So that was pretty nice.
Not the exact same, but
Well, I mean, if you ignore this little 1 right here. then it's the exact same thing. That part was the exact same.
So what could we do in the code to make the Maple Euler's method solution go out one more decimal place?
That's a good question.
Anybody want to help? I know somebody knows.
Does that work?
I don't think so.
Yeah, I'll try my best.
How can we modify his code to
I believe you
include?
can just do digits equal and then the amount of numbers.
Yep. And for this one, it's
Digits is spelled D-I-G-I-T-S.
D-I-G-I. Thank you.
No problem.
and this is literally asking for no, don't. Oh boy. Oh boy. Well, we're going to be here for a while. Oh boy. Okay. So Maple will give up, of course, because it can't show 100 decimal places on the screen. Digits represents number of significant figures. That's the way most of us think about it. So if you did like 5 significant figures, that should be plenty. And so now you can see, yeah, that's the, at 5 decimal places, there you go, at 5 digits, that works. So that digits command is important. And I talk about this in one of the videos where I say, once you get to making predictions and your step size is small enough so that the difference from one step to the next is out like in the 4th or 5th decimal place, if you're rounding to the 4th decimal place, then you're not actually going to see any difference between steps, right? You're losing information. So as your predictions get further out in terms of the number of decimal places required to see them, then you got to be careful with the number of digits that you're using. And so Maple will give you as many as you want, maybe not 100, but it'll give you up to, I've seen 15 pretty easily.
Yeah.
So cool, handy. So one question for you, how did you know? No, actually, I'm gonna reserve that question for later on. So congratulations, that's part B. How about part C?
So part C was using your exact solution for part A. How accurate is your approximation for part B? And I concealed this one because it was just too technical. I didn't want to like overwhelm anybody. So we officially concluded that the approximation was meh. So we got, Euler gave us.
Excuse me?
Or it was my water Euler gave me a 2.6 and the real answer was like 2.1. And so not the greatest.
What does that tell us about making predictions for this function with that particular step size?
It's a pretty meh.
Well, you think about it, your curve is a sine curve, right? And so that sine curve changes direction relatively quickly. And if you take a step of 1/2 unit, and you kind of go in that direction for 1/2 unit, you are way off the curve by the time you get there. And then it's going to say, oh, now go this way. And so you're way, way past being connected to the curve at that point. So Euler's method, if you're using too big a step size for a really tight curve, then you're going to blow past the solution. So, and what about D? Use a smaller step size.
D is when we ran out of time.
Okay. So if you copy and paste that code right there, and then we'll just change. Now, how do you change the step size?
Just num steps to 12, right?
Sure. So you
double?
double the number of steps, which does what to the step size?
What's that? Sorry?
It's okay. If you double the number of steps, what does that do to the step size?
It cuts it in half.
Yep. You're going the same distance, but if you take twice as many steps to get there, then you must be going half as far for each step. So let's run this bad boy and see what we get. And so Maple is able to run up to 2, and we're able to see on the screen up to t equals 2, but we're not seeing all the way to 3. So anybody want to step in and help? How do we get Maple to show all of the table? Show more. No, it's not going to work. Be nice if it worked that way.
I think you can just right click and show all, can't you? Or see all.
You can either right click, depending on the version of Maple that you're using, or it'll pop up, yeah, in the context panel. And so if you scroll, you go down a little bit further, show all. There it is. If you do that, and then you want to be able to see the entire table. And so now take a look. Our solution is now, our guess, our approximation is now 2.3891, which is better, but still not great. So one thing you can do that I think is really helpful for this, I mean, the table is nice because you get the actual numbers, but take a look at doing, instead of output information, let's try output plot and see what we get. So go up and change your output code from output information to output plot.
Wow.
So you can actually see that, wow, Euler's method is trying to follow the shape of that curve, and it does a pretty good job following the shape. It's just like behind it just a little bit. It just kind of like doesn't quite keep up with that number of steps.
This one for comparison.
Yeah, you can try it and compare. Yep. It's handy for being able to do that. And so, whoa, way different. And if you take a look at the scale on that graph, that second one is only up to about 3 or a little over 3, and the one above is all the way up to like 3.2, almost 3.5 maybe. It's getting up there. So you can see that the second one is doing a better job of approximating, but it's still not that great. And if you change num steps now to, I don't know, double it again, see what happens. And you can see, oh, we're getting better. The solution's getting better. But still, I mean, if you had to do 24 calculations by hand, you'd be pretty sick of it, right? You'd be like, I don't know. And this is why in the old days, you would, if you were the engineer who was trying to approximate the curve that your rocket trajectory is going to follow, you'd say, I don't want to do 100 calculations. This is going to take me all day. I'm worth more. I have better things to do with my time. So I'm going to take all of my paperwork and I'm going to take it to the computer, which meant going to another building that was filled with floor after floor after floor of floors full of tables where people sat with adding machines and sine tables and cosine tables and log tables. And all they did all day was calculate. They were computers. If you've ever seen the movie Hidden Figures, you ever get to see the movie Hidden Figures? It's a great movie. Those women were fabulous mathematicians, but they were computers. That was their job, to slog through all of these calculations. I don't know about you, but I would go crazy if I had to do all those calculations. That would drive me nuts. But it was an important, very important part of the work. And so they had to know whoever they were handing the calculations off to, they were going to do a good job. So not only were the people who ran these things computers, but they were tip-top mathematicians. They had to be, because they were trusted with these calculations. And of course, you didn't just run it once. You had multiple people run it in all at the same time and check the answers afterwards. The calculation that you just did would take a group of people out to 6 decimal places, would take a group of people somewhere in the area of an hour to not only run it once, but to double check it and cross-reference. Like that with Maple. Now, I know you're not impressed, and old people saying, "Do you kids have it so good these days?" is probably not all that impressive to you. But it's worth pointing out that this is an amazing tool that you have at your fingertips, right? It does a tremendous amount of calculations. And when Maple takes 10, 15 seconds to do calculations, you should be thinking, oh my God, there must be tremendous amount of calculations in the background here. So if you ever get Maple working on an Euler's method problem and it just kind of hangs, it's like you've been waiting 10 seconds, that means this is a lot of computations. And doing it by hand would have been, for all practical purposes, impossible. Cool. So how about 1.4 number 2?
All right, so screen share. All right, so there's two parts to it. There's A and B. Number of steps I think it was delta t equals 0.025. So we divided by that, and that gave us number of steps, which was 40. We plugged in Euler's equation, and we went from digits five digits not speak today. 5 digits past the decimal point.
Nice. So it looks like our
What we
prediction.
got.
Yeah, go ahead.
No, I'm good.
No, I was just gonna say it looks like our prediction is pretty close, right?
Yeah.
And it's to the second decimal place where there's a difference in digits. So rounding to 5 decimal places, that seems reasonable. If it were the second decimal place where you see a difference in digits and you round it to the second decimal place, that's not given enough digits, right?
Right.
So you use your common sense for this and you'll figure it out. So
And then our second one's where we had a bit of trouble. So in the classwork thing, it said we were going from -2 to 2, and then we got the correct number of num steps right, but
Yep.
we're not sure exactly how to go from -2 to 2 on this.
Yeah, this one was I threw you a curveball on this one because the code for Euler's method says you have to have an initial condition, and that's where Maple starts. It starts at, in this case, a t-value of?
Is it was t-value of -2, but
For your initial condition, what's the t-value for your initial condition?
t-value it's 0.1. I'm getting this wrong. Initial condition. -0.5.
That's the output. That's the y value. What's the initial condition t-value that produces that?
0.
So that ordered pair that you're given, that second thing right after the differential equation, the initial condition is saying at a t-value of 0, you know the y value is -0.5.
Right.
So Maple says, okay, I'm going to start at t equals 0. The next thing you tell it is, I want you to go to a t-value of something, but you can't give it a range. You can't say, I want you to go to a t-value of -2 to +2. You have to say only one number. So that means you have to start at 0 and you can go to 2. So if you change that from t equals -2 ... 2, if you change that to just t equals 2, and then rerun it. And I don't think you need to do 40 steps for this one, do you?
Hold on, because what number was it? It was so
For 2b, I'm looking at it on the classwork, and it says delta t of 0.1, but that's a delta t of 0.1 to go from -2 to +2.
So yeah, we went with 4 divided by 0.1, and that's where we got that 40 from, because we went from -2 to +2 is 4 figures.
Okay. So, but remember, going from -2 to +2, that would be 40 steps. But the code that you just told Maple to do is to go from 0 to 2.
Oh, so I should do 20 steps.
So you only need 20 steps for the code that you entered, which is going to give us, a very different answer, right? Because the step size will wind up being a little bit bigger because we're taking fewer steps.
Okay, so they're pretty close up to about the second decimal place. I did digits equals 5 on these ones, or I tried digits equals 7 just to see if we got a better answer.
Sure. And so while he's doing this, basically what we've done is we've divided up our interval from -2 to +2. We have a initial condition that starts in the middle of that interval. And we want to know what's going on in both directions. And so here's the prize that you can earn. Can you figure out a way to get Maple not just to go from 0 to 2, but to make Maple go from 0 backwards to -2? Can you make Maple predict backwards in time with Euler's method instead of just forward in time? Because if you can figure out how to do that, I have a shiny $2 bill that I'll mail to you. And I'll make sure it's not even covered in COVID. Because I've never figured it out. Now, I haven't put, to be, complete honesty here, I haven't put that much time into it. But the reason I included that example in the classwork is to show you that if you start, for Maple, if you start anywhere other than the beginning of the interval and go forward in time, Maple doesn't like that. Or at the very least, I've never found a way to get Maple to like it. So those of you who are code hounds and you really want to get in there and look for things and find out, I would love to know how you do it. I'll make it worth 5 points back on the last problem set if you want to do that, if you can figure it out. I'm tossing that out to everybody. Don't get too excited. So is everybody clear on the problem of classwork 1.4, number 2B? Everybody clear on what's the trick? What's the difficulty with that setup? Can I get a hand clap or a thumbs up? We got both, right? Not bad. Okay, so who had number 3 for 1.4?
We did.
We did. Okay, fire away.
I'll share my screen.
Feel free.
I'm fixing B right now because I think I know the issue.
Oh, okay, good. It's always nice to find what happened.
Okay, so we're using Euler's.
Can you zoom in a little bit?
Oh, absolutely.
Excellent pronunciation. Wow. There we go. Yeah, that's good.
Awesome. So basically, for A, our problem was our differential equation is basically this right here. And then we just said for A is y of 0 is equal to 2. So our initial condition is 2. Then t ranges from 0 to 2. And then our steps is 0.5.
Which means number of steps is going to be
4.
4. Yep.
Yep. And then I just plugged it in. And then our Maple solution is 5.2, and our Euler's method is 5.8.
Cool. And so for part B, it says, okay, use the same equation, but a different starting and different ending point.
Yep. So then just at y of 1 is equal to 2, and then we're going from 1 to 3, so I didn't have to worry about the left side. So yeah, just 1 to 3. I just said end at 3, and then num steps is 4 again because we're going 2 at a step 0.5, and then yeah.
So what do you notice about those two Euler's method outputs?
They're the same.
And so part C is, what do you make of that? How do you explain the fact that starting at 2 different initial conditions, Euler's method predicts you'll wind up at the same height?
I'm just going to take an educated guess here
Excellent.
and say it's because you're shifting on the horizontal axis.
Because we have a differential equation that is what kind of differential equation?
No, yep.
What is it?
Autonomous.
Ding, ding, ding. Nailed it. You were starting to say it there. I really thought you were going to get it there. She's like, and I'm like, autonomous, yeah, throw it in there. So because the differential equation is autonomous, think about what this means for the DE plot. As a matter of fact, what I want you to do is go ahead and let's create a DE plot underneath here for this differential equation.
Oh, I'm not typing. Oops.
It's okay. So And you can copy and paste the equation from up there. Just go up and grab it. There you go. Yep. And then the code would be after that, comma y of t to identify the differential or the dependent variable, comma t equals, let's just go from 0 to 4, something like that. And then we don't need an initial conditions. We can add them later if we want. Let's go y equals, well, I don't know, 0 to 4 as well, just for giggles. Actually, no, let's go 0 to, we need to go higher than that, 0 to 6. We'll do 0 to 6. And then let's give it a shot. Let's see what our differential, our slope field looks like. So move your cursor so that you are right over the first initial condition. Y of 0 equals, what is it? Y of 0 equals 1? Is that what it is?
It's 2.
Oh, y of 0 equals 2, sorry. So y of 0 equals 2. So hover your mouse right over y of 0 equals 2. So if you started there, do you see the shape of the curve that would have to follow?
Mm-hmm.
Right? It would have to kind of go up and go like that. But do you see how that if you move horizontally so that it's y of 1 equals 2, the shape of the curve from that point, it's the exact same.
Same, yeah.
So you've discovered that it's an autonomous differential equation. So therefore, you're predicting 1t or 2t units later, you're going to have the exact same height prediction. And now exactly that's what I was going to have you do next, is throw in an initial condition so we can see what this curve looks like.
Oh, I forgot another.
Yep. So those of you who are kind of watching this, make sure that the code, oh, you need to have it equal something. So y of 0 equals 2.
There we go.
There you go. And y of 1 equals 3. No, equals 2. And then close the bracket, comma, and then get rid of that 2. You have an extra 2 there you don't need. And now we have.
Oh, I want to do line color.
Yeah, I hate that pukey yellow color. I think it's roughly maize, which is a disgusting yellow color anyways, so. No, nobody's gonna take a bite on that one? Okay.
Nice. Is that from Grown Ups? Is that what you reference?
No, I was joking about there's a school down the road whose colors are
Oh,
pukey yellow and blue, but you know.
Yeah.
I figured Austin would catch me out on that, but. So you can tell by those two graphs that they're the same curve, just shifted horizontally. And to connect back to what Emma was saying, they're going to predict the same height after the same amount of, shifted time, right? So it kind of comes full circle. Autonomous differential equations look the same all the way across. So what about differential equations that are kind of the opposite of autonomous? What if a differential equation doesn't depend at all on the dependent variable? What if the right-hand side of the differential equation is a function of the independent variable? What do they look like?
I have no idea.
Anybody want to venture a guess? Imagine we have dy dt equals t squared plus 3t. What's its slope field going to look like? Okay, here's what I'm going to have you do. Everybody, and so stop sharing your screen so that everybody doesn't see it. But I want everybody to hop on their Maple right now and take a look at what the slope field. So that means you got to do a DE plot of the differential equation dy dt equals t squared plus 3t. We'll just call it that. Let's produce that slope field.
What did you say it was again?
Dy dt equals y squared plus, equals t squared plus 3t. And while you do this, I'm going to shunt you all into breakout rooms. I'm just going to give you like 2 or 3 minutes to see if you can all agree what's the defining characteristic of something whose right-hand side depends only on the independent variable. So I'm gonna put you in the breakout rooms here. Well, only for a couple minutes. Shoo, be gone with you. Oh, Austin, Mr. Connection issues. There, I assigned you to breakout room. I'll give people a chance to come back. I'm going to text my mother before I forget. I'm going to hit pause.
Accidentally hit the button. Wow.
That's okay. You were coming back anyways. Only a matter of time. So, how's Austin?
Austin is doing okay. That second problem set wasn't nearly as confusing. I told everybody with you teaching, it takes about one problem or one homework week to kind of get used to what you're
Yep. It should do that no matter who's teaching, right? Because every class, especially at this level, every class is new. And so new material, new approach, it's just going to be different. And it's going to take time to get used to it. Plus, I think if you give yourself enough time to actually get the problem sets thoroughly done, you'll be
Well, I
better
did.
off.
Almost. I just missed that one trick question you threw at me, and I was so irritated about it. I'm like, duh.
No, I meant problem set 1. I don't think you gave yourself enough time to finish that one up.
I didn't? I don't know.
I don't think he eats paper. That's what I was about to say.
There you go. He doesn't eat paper.
Before we were interrupted.
Okay, welcome back. So, what did you notice? Anybody want to take a stab at explaining if I give you a differential equation, dy dt equals some function of t alone, what should I expect the slope field to look like?
All of the vertical slope values would be the same.
If you look at any particular value of t, it should be the exact same slope everywhere up and down. Did you guys see that in the slope fields that you created? Quentin, just nod. There we go. Yes, excellent, good. So that's the important thing. That's the key thing. If their slope field depends only on the independent variable, then as you look this way, all the slopes look the same vertically. If it depends only on your dependent variable, as you look this way, all the slopes look the same across. And what happens if it depends on both? Well, it's messy, right? No matter where you're at on the plane, you have to say, hey, what's my x coordinate and my y coordinate? Throw that into the differential equation, and it spits back, oh, you should be pointing in this direction, or you should be pointing in this direction, or you should be pointing in this direction, right? The differential equation is a map that tells you at any coordinates what direction is the solution pointing. Right? That's the graphical interpretation of a differential equation. And the slope field is the picture that we can see all of that on. And again, the slope field was something that we couldn't generate easily or quickly, even 30 years ago. When I was an undergraduate, I would have killed to have something that could generate a slope field because I was doing it by hand, calculating, okay, at this point, at this point, at this point. Then you had to get out your protractor and guess what direction. Ugh, God. Ugh, no. So Maple creates that for us so we can use a graphical view of a differential equation to see how it's behaving. And if it has equilibrium solutions, then you should see those horizontally. Or if it happens to be a particular point, you might see solution curves kind of roaming around a particular location, right? There's all kinds of weird stuff that happens on these graphs. So we are now getting to the end, right? We only have like 2 minutes left. But what I want to do real quick before we finish up is I'm going to share my screen with you, since you guys have been sharing screens all over the place. I'm going to share my screen with you just so that you can, so we all can kind of point in the same direction. We've got a lot of ground to cover. You have some videos to watch before next time. I've got some videos to make, and I've got to make sure my computer stops eating all the videos that I keep making. I don't know why it's doing it. But please keep in mind down here for homework that you've got videos to watch for next time. You've got a problem set over 1.2 and 1.3. So no Euler's method on that problem set, but definitely slope field stuff. You've got problem set 4 that's going to be due on Monday of next week, along with investigation number 1, which is all about the logistic curve and creating a slope field and making predictions from that. So I didn't even put a link to problem set 5. You've got enough to keep you busy. But between now and Wednesday, you've got some videos to watch, fill in those notes so that when we show up on Wednesday, we can work on some stuff together, the classwork together, right? Now remember, the classwork is like, it's practice. You show up for practice. And yeah, you're a little sore after practice. And yeah, you might not have played your best at practice, but it's just practice. When it's game time or when it's scrimmage time, you know, I want you to do better, but you have to practice in order to do better. So keep that in mind. If you want to stick around and ask any questions, you can do that. Otherwise, I will see you all late, my friends. I'll stop sharing the screen if I can figure out how to do it. Oh, it's over here. Stop share. So I'm going to stop recording, and if you want to stick around and ask any questions, you can. Otherwise, I'll see you on Wednesday.